Okay, welcome everybody. So the purpose of this lecture series is to give brief introduction to superconducting and superfluid phenomena with main focus on superconductors. So my name is K.Pomorski and I am CEO of Quantum Power Systems company, and also I developed quantum technologies, and somehow it's necessary to um, to have insight into superconductivity as manifestation of macroscopic quantum effects. So, so let me start this story uh, of discovery of superconductors and superfluids, and then give you some insights. So, I will extend methodology which I am applying step by step. So today is just phenomenological description. So basically, the story is starting in 1908 when a liquefying of helium was obtained. This was done by Ones, and was very interesting because he got this equipment from Jagiellonian University. There was uh, uh, there was developed uh, cryogenic equipment by Jagiellonian University since there was famous discovery of liquefying of oxygen and nitrogen, and then this equipment has been the patent was sold to Netherlands, and this was equipment cooling equipment was developed further, and then there was discovery of superconductivity in 1911, and this was quite much in contrary to commonly known paradigm of uh, of Kelvin. Kelvin basically assumed that at very low temperatures we will have uh, the electrons will be frozen. So if we cool down the sample to sufficiently low temperatures, we're supposed to witness infinite resistance. But this was not exactly the case. And the when the mercury sample was taken, it turns out that its resistance dropped by a few orders of magnitude. So basically the new type of phenomena has been discovered. Actually, the assistant of Honest was fired since Honest suspected of very bad performance of from his side. But actually, he realized that this is very breakthrough that contradicts the classical physics predictions in a way. So also it was like discovery of quantum because this is associated with quantum effects. So this is also quantum phenomena. So this was discovery of first macroscopic quantum phenomena. And then the story was continued, and in 1933, the Meissner effect has been discovered as the Meissner and Oschenfeld. And this was the phenomena when the magnetic field was pushed out of the superconducting sample. So this phenomena we also somehow some superconducting state is defending itself from entrance of external magnetic field. So in a way, superconductor defends its ground state, and um, and then the London theory of superconductivity was discovered. London theory um, basically implies that current density is proportional to vector potential. And this is quite unusual because we usually learn from the university or from the high school that current density, electric current density, is proportional to electric field. So in a sense, the realism of existence of vector potential has been demonstrated. And then so it will turn out later that you can get this London equations from through the model of electrical resistance when you have a scattering of electron on uh, on crystal vibrations, and then when this time of life of undisturbed electron goes to infinity. So basically, this is this is London theory that is a kind of dual to, in a sense, to Ohm law of resistivity. Actually, both laws will be preserved at a certain degree in superconductors when we will come into details. And then there was 1950. There was uh, there was um, theory of phenomenological theory of superconductor and non-superconductor phase transition that was described, and in this theory, basically the second order phase transition was described in very phenomenological way. So this was actually this is like the Gisbrough-Landau equations has been invented in that sense, and this is so this phenomenological theory of superconductivity has allowed to describe interplay of vector potential, current, electric current density, and superconducting order parameter strength. So, and later, this theory also point out the existence of vortices in superconductors. So, then the BCS theory has, but this was phenomenological theory, like Landau theory of phase transitions, when the ferromagnetism is explained, is also worth of mentioning in this context. And then in 1957, the BCS theory of superconductivity has been invented. So this is microscopic theory of superconductivity. Actually, it's still phenomenological. Nevertheless, it points out the existence of of superconductivity. So it was invented by Barden, Cooper, and Schrieffer. So then, at first, Cooper has created the concept of has introduced the concept of Cooper pairs. So when two electrons are paired, so when they are paired and they create quasi-boson, and this quasi-boson has tendency to go into Bose-Einstein condensate, which takes place, but when it takes place, the electrons start to be at shorter and shorter distances, and at some point they start to feel the electric charge. So this is not full Bose-Einstein condensate. Nevertheless, you can understand superconductivity as first stage of Bose-Einstein condensate. And there was a Barden and Schrieffer that also assisted in this theory development. That's why it's named BCS. There is a couple of layers of theory of superconductivity. I would say BCS theory is quite deep, but this is not the deepest possible path. And nevertheless, it's quite effective, especially for low temperature superconductors. So there is electron pairing mechanisms that are described in a different way, like by Hubbard model, for example. So there is an Eliashberg theory of which gives much more detailed mechanism of electron pairing. And still, the puzzle of high temperature superconductors is unresolved till nowadays. So it's still work in progress. So at least more than 5 Nobel Prize has been already awarded due to nature of superconductivity. So in 1957, this theory has been invented. So people start. So this is like superconductivity in simple materials like niobium. Uh, can be well described, and then is the theory of tunneling, and this tunneling theory has been, let's say, Josephson effect has been invented by Josephson, and verified by Javert. So there was shared Nobel Prize to them. Actually, you can see those guys over there. So the first one is Honest, then there are Meissner effect in London, and then you have this. So there are tunneling experiments. So the Josephson effect is the phenomenon when two superconductors separated by non-superconductor when they can couple, and then there takes place tunneling of Cooper pairs, the paired electrons via non-superconducting region, and then for a long time there was no much invention. There was invention of various types of superconducting electronic devices, but in 1986 there was another Nobel Prize, and then there was for Bednosh and Miller for the discovery of high temperature superconductors. Basically, they are categorized as superconductors that are described by non-BCS theory, and superconductors that I would say usual superconduct beyond 30 Kelvin. So there is this discovery of high temperature superconductivity, and this was quite. And also, these materials are high anisotropic, contrary to low temperature superconductors. Like materials like IPCO have AB plane and C plane. So, and there is much different effective mass of electron and so on. So this is definitely different mechanism of superconductivity that is still debated since time of discovery. Especially at high pressure, there's a lot of new phenomena in field of high temperature superconductors, but I would say that especially superconductors at high pressures, they can superconduct in relatively low temperatures, in relatively high temperatures. So like minus 100 Celsius degrees and so on. Then there was another Nobel Prize, another Nobel Prize admitted to because of Ginsburg and Leggett for theory of superconductors and superfluids that is interconnect. Yeah, there is some chat question. Yeah, so we will talk about these chemical compounds later. There is a question. Yeah. So this is how it has started. And let me move on. So what are main manifestations of superconductivity? Well, first signature is zero resistance at superconducting state. So if you have ohmic resistance that is somehow for metals is increasing with temperature, like usually in a kind of linear way, and a sudden drop to zero, it's possible indication that you have discovered the type of superconductor. Then there is expulsion of magnetic field from superconductor. So otherwise, you can say that magnetic field doesn't like that the superconductor doesn't like magnetic field. This is not always fully true because we have S-wave superconductors. We can have also superconductors with existence of Cooper pair in triplet state. But in first approximation, expulsion of magnetic field from superconductor is indicator that superconductor is that given material is superconducting. Actually, what happens is that there's the screening current is induced in superconductor, and the screening current that has no dissipation. This is like superconducting current. The screening current will compensate the magnetic field that tries to penetrate. So basically, it creates counter field and this counter field is going to make net magnetic field zero or close to zero inside superconductor. Of course, this phenomena takes place till certain strength of magnetic field. And the idea is that it's also very important that in Cooper pairs, the electrons are paired in opposite way. So net spin of Cooper pair is zero. So when there is entrance of magnetic field, this magnetic field tries to orient spins in one direction. So it tries to break down the Cooper pair. So that's this screening effect takes place under certain strength of magnetic field, because otherwise superconductivity can be broken down and superconductor can transfer to non-superconducting state. What is important is that there's also this phenomena is very important from the perspective of levitation. So the phenomena of superconductor levitating over a coil that produce magnetic field or over ferromagnet is also well known and exploited in high-speed trains and so on, for example. Okay, then there is expulsion of magnetic field from superconductor, also known as Meissner effect. Then there's characteristic heat capacity drop, like lambda, a kind of lambda, specific lambda shaped transition, and this is actually occurring for both super fluids and for superconductors. This characteristic heat capacity drop. Then there is levitation of superconductor, which I have already explained. There is quantization of magnetic flux, and there's occurrence of quantization of magnetic flux is basically the phenomena which says that if you have superconducting ring, you can enter multiplicity of magnetic flux into it, and so magnetic field stream flux, flux is quantized. And so this has to do with that after rotation over 2 pi n, your wave function needs to have the same value. This is the more exact reasoning will be specified later by me. Okay, so this quantization of magnetic flux, which also has to do with existence of Abrikosov vortices in superconductor. And there is Josephson effect, and this is quite important to mention, as I already did, that we have a first stage of Bose-Einstein condensation. Actually, superfluidity, superconductivity, and Bose-Einstein condensate shall be interlinked. And it's also quite interesting to recognize that Josephson effect is also can occur between two Bose-Einstein condensates. That's worth of mention. All right, let me move on. Then main manifestations of superfluidity. Yeah, maybe one more thing. Let's say the superconductors basically doesn't tolerate magnetic field. It doesn't tolerate electric field, and you always control magnetic superconducting state mostly with magnetic field, or more exactly with vector potential. Okay, now let me move to main manifestation of superfluidity. It's lack of viscosity. So basically, liquid with high viscosity is honey, and liquid with low viscosity is, or with zero viscosity, is superfluid helium. So, so what does it mean that when you start to rotate, if you have a cylinder, you start to rotate the liquid in cylinder, it can rotate forever. It's almost true. Let's say experimentally, this simply means it can take long years or long time to reduce the speed of rotating superfluid. There are certain phenomena when the liquid you place the superfluid in a container, and this liquid can go out of the container. Even let's say contrary to gravitational laws, because you can say that it's supposed to stay, but this you have to describe this in more detailed way by Gross-Pitaevsky theory, which is similar to this Brandov theory actually. And yeah, so there's a Fontaine effect, also known so creation of temperature gradient would affect sudden movement of superfluid. There's also Josephson effect possible in superfluid systems. So basically, if you cool down the system below 4 Kelvin, then you can observe superfluid phenomena. That's the first thing. And also, you can also observe superfluid phenomena for helium-3 when the atoms of helium are having net momentum, having spin 1/2 the pair. Yeah, so I will mention about this in more detail later. And this is also worth mentioning that you can build Josephson junctions with usage of superfluid liquids, let's say, but this is very hard and quite impractical. Um, impractical from the point of view that at least if you have small dust particles and you have Josephson junctions in space, when small dust particles hitting your device, you can detect its such event by superfluid Josephson junction. So you can spot such very tiny events. So this is like complementary to Josephson effect in superconductors, where you can detect very small magnetic fluxes by magnetic field by Josephson junction. So you can detect very small changes of magnetic field. There's also phenomena of, of Josephson junctions in Bose-Einstein condensates, but I will not dive into this topic. I'm just right now mentioning. All right, let me move on. Yeah, so there is a phenomena of there is a phenomena of you have superconducting ring, there is magnetic flux, and so there is a flow of non-resistive superconducting current. Um, so what happens is that here we have this current can flow forever, and this phenomena which I describe and which I am describing also uh, this is the way to store magnetic field energy in superconductor in general. So let's say you can store electric energy on the moon because it's quite on on the dark side of moon that is not under influence of sunlight. In such a case, you have low temperature, and you can use high temperature, low temperature superconductor which will superconduct in this state. And then you can enter big current which will last for a long time. You can so that's a safe way of storing energy. All right. This phenomena of flux quantization is also very important from the usage of rapid simple quantum flux electronics and the way of implementing of classical electronic in superconductors. So this phenomena is important. So in superconductors, you have quantization of magnetic flux. In superfluids, you have quantization of momentum, angular momentum. And having quantization of angular momentum, well, can have its uses, as I already mentioned, in construction of very sensitive detectors of small collisions. All right, so that's brief. I will come back to this picture many times in future, but it's now right now I try to build your conceptual space, how to perceive certain uh, physical phenomena that are occurring. All right. Yeah. So this is now the phenomena of non-superconductor versus superconductor. If you have a metal that is non-superconducting, usually it has resistance. So you have this as we've given it with blue curve. So it does this resistance is increasing with temperature. So there is residual resistance at the ground state. There is However, there is, in case of superconductor, you have such phenomena as with red curve described. And there are TC temperatures, temperature of transition from non-superconductor to superconductor state. And so this is like usually sharp transition. And usually it's, so one way is to magnetic susceptibility is another way to study it. So you can have usually you have such phenomena that if sample is above critical temperature, magnetic field can easily penetrate it, as it is indicated here. And once it's cooled down, usually magnetic field tries to flow around of superconducting ball or material in general. Yeah. So this is this already mentioned physical phenomena are expressed by pictures over here. All right. Then, if you start to study, there are first type superconductors and second type of superconductors. And first type of superconductors basically, okay, so this is what happens is above TC temperature, is left side. If you increase magnetic field, it starts to, okay, if magnetic field is of low value, it is like flowing around, and after having certain strength, it can punch locally. What happens is that the generation of magnetic vortices inside superconducting sample. So like Abrikosov vortices, essentially. And there was this actually Nobel Prize given to Abrikosov for this discovery. And the core of Abrikosov vortex has reduced or zero superconducting state. So the core of, because of vortex, these regions are quasi-normal state. So this means there is almost zero concentration of Cooper pairs over there. And also these vortices can move across the superconductor. All right, so you have just picturized so this is, middle picture is a Meissner effect. It's like, so this repulsion, and there's of course still a Meissner effect, but then at some point, so if you increase number magnetic field strength more and more, you have more and more vortices, and at some point, so higher concentration of vortices, and at some point the whole superconductivity disappears, so the whole state transitions into normal state. All right, so this is how it is picturized, this phenomenon. And of course, then we need to employ mathematical models like London theory, then Ginsburg-Randall theory for this picture, then Bogdanoff-de theory, Usadel equation, Eigenberger equations. You can even use Kaldish green function technique, especially for the case of moving vortices. And then, yeah, so you can also play with, it's more challenging to play, but you can even play with Hubbard model of such situations. So in general, there are certain layers of mathematical description that are possible, but of course, it's quite straightforward to use Ginsburg-Randall theory to describe this phenomena which are given here. All right, I will not dive into too many details, which I will bring later. All right. So what's the phenomena of Meissner effect? So you have magnetic field. Let's say it's parallel to superconductor. Then there is a direction of superconducting current that is induced. If you deal with analogies, okay, Meissner effect takes place both for case of DC magnetic field and AC magnetic field and combined version DC and AC magnetic field. But if you try to refer this effect to another phenomena that is well known to you, you know that metals, doesn't matter what type of metals, they react in a certain way to time-dependent magnetic fields. If you subject metallic ring or a metallic piece, replace this metal into time-dependent magnetic field, what happens is that there is induced current which tries to protect metal from changes made from AC-dependent magnetic field. And this is very much similar to Meissner effect, but Meissner effect is occurring also for DC case. So this just I tried to bring certain phenomenological intuition in understanding and perceiving the Meissner effect. All right, so that's just examples. Of course, magnetic field can punch perpendicular, or it can be in such situations as over here, and then in both cases there is reaction of superconductor. If you have DC and AC magnetic field present, and here, then you can expect that there will be superconducting current, or the current of superfluid electrons, you can say, and current of unpaired electrons present, which the second one will bring certain level of dissipation, but we will talk about this in new coming during new occasions. All right, so let me move on. Then you can probe the superconducting state, and basically, if magnetic field is in certain values, so it doesn't exceed certain strength, you can have superconducting state. This is denoted by orange color. Then if you have temperature below critical temperature, you can have superconducting state, and if you have current density below certain critical density, you can have superconducting state. So if you exceed current density above certain value, then what happens is that the superconductor moves out of superconducting state. So what is very interesting is, in case of superconductors, you have very high possible density of current that can flow via superconductor, and it does not overheat or does not heat at all. Just to give you example, you can have rectangular shape cable, and if it's superconducting, it can have, let's say, cross section of 1 centimeter times 1 centimeters. So this 1 centimeter square. You can send even very big currents over that in terms of almost few amperes will not hit your cable. The problem that happens with superconducting, so you can have high power superconducting devices, and high power superconducting devices has been also produced in Poland. Majka from Lublin, Professor Majka. He was fault current limiter, so he was able to build devices that the current limiters that turns off when there is big current flowing via them. And this devices was quite famous worldwide. Yeah. All right. So there is another question.
So,
Yeah.
so I have a question.
Go,
My question,
yeah, go ahead.
my my question is there a way of determining whether a certain substance is going to be first or second type superconductor theoretically by knowing its structure without any measurements?
Probably not. At least there is DFT, density functional theory, that gives you. So the there are two characteristic lengths valid for superconductors. First is penetration depth of magnetic field. So magnetic field penetrates and is damped. So it's characteristic. So it's exponential decay of magnetic field. And second phenomenological parameter, which is very important, is the size of Cooper pair. So this can be translated that. Oh, there is some other. So there is a situation when. So there is a situation when you have superconductor and non-superconductor interface. So the ratio between those two characteristic lengths decides whether superconductor is first order or second order. And at least I'm not aware of existence of any theory which allows you to predetermine this, this is the size of those two characteristic lengths. But you can somehow detect experimentally whether you have existence of vortices or not, because vortices can move. They can move, and when they move, also they also create a dissipation. So I will come into more details with more details on coming lectures. But at least in accordance to my limited knowledge, I I don't think we have a tool that can give you unique predictions. Um, Nevertheless, especially for not too complicated materials like mercury or simple metals or metal alloys, you can get more and more predictions using density functional theory. So you can predict a lot of material properties by calculations. Like there's conditional theory using, and there is various modeling of those materials. But those materials are quite those materials are quite simple. And but if you do very complicated materials where you have 10 elements in one cell, crystal lattice cell, like in IPCO, high temperature superconductor, you lose quite much the control of predictions. So you have to do experiments and iterate trying many things. So I'm afraid that there is no universal prediction tool for that. Um, yeah, but that's nice and interesting question. I hope I have answered it. There's another question from audience. Can I talk about energy balance and transfer during the phenomena of superconductivity, noting in nature's moves? No, yeah. So yeah, I can come to this to this. Uh, I need to write down the equations, the specific equations. I will try to answer to this question in quite steady way. All right, let me move on. So this is like thermodynamical diagram of superconductors. So you have three controlling parameters: temperature, magnetic field, and current density. So you can tune superconductor and superconducting level. And of course, if you have zero magnetic fields, zero temperature, and zero current density, you have the strongest superconductor that's overheat. Once you are closer to the surface, the superconducting become less and less strong. And close to critical temperature, there is linearization of critical magnetic field. So critical magnetic field necessary to destroy superconducting state becomes smaller and smaller when temperature becomes higher and higher. And very close to critical temperature is scaled by such a formula. All right, it's just phenomenology. Okay, let me move on. All right, and then superconductors has energy gap. So you have state which was normal state. So you have like metals at ground state or low temperatures. You have
Zaprosili mnie, żebym uczestniczył.
uh, please mute yourself because there's one person talking right now. All right. So okay, so you have all levels filled till Fermi level, and this is normal state. And above Fermi level, it's empty. So this is typical metal. When this metal transits, and also I forget to mention that for some materials, if they're not subjected to pressure, they don't superconduct. And if pressure is there under pressure, or very high pressure, they can superconduct because pressure changes the crystal lattice structure. So there is some theory that all materials, or metals at least, will superconduct at sufficiently high pressure, but this is just hypothesis that is not yet proven, and it's hard to prove it experimentally because sometimes this critical temperature can be very low. So what happens is that you have like mercury that has a field until Fermi level is achieved, and then above, when it starts to superconduct, small gap, energy gap appears, and this gap was predicted by BCS theory, and then the size of this gap is quite small. So you have aluminium 0.34 millielectronvolts. So of course you can see this gap value by that certain by absorption of certain wavelengths, and then you have specified this value of this gap in this table. So you have niobium 3.05. Niobium is used for rapid single quantum flux electronics, and this is for PB mercury. We have 2.73, and so on. And then we have for other materials given here. So it's this value of this gap also means is a measure what voltages is destroying the superconductors. If you so this is if niobium a value of band energy gap is 3.05 electron-volts, it simply means if you apply voltage 3.06 volts, this niobium will transit from superconductor to non-superconductor. So this is also a measure of tolerance of superconductivity against external voltage applied. And then this value of this gap is temperature dependent, as specified here by BCS theory. And this is well, as you can see, there's a formula from BCS theory which interlinks value of this gap with critical temperature. It's given here, and yes, and that's a BCS curve. You have it, and this is for different niobium tin. You have the plot of theory and experiments. So BCS theory is able to work well. It usually works well to materials below 30 Kelvin. Actually, this also BCS theory has also imposed the predictions of that high temperature superconductors supposed not to exist, but they were discovered to exist above 30 Kelvin. So this BCS theory starts to break down. So clearly, the mechanism of superconductivity in high temperature superconductors is much different from BCS theory. So sometimes very good theory can work onto certain scope. All right, let me move on. Then there is a BCS theory of superconductivity, and well, it's about lattice and electron interaction. So you have, especially in metals, you have cores, atomic cores, which are charged positively, and you have Cl electrons. And basically, if there is a moving electron, there is electron phonon interaction and Friedrich Hamiltonian. But basically, this moving electron is attracting two cores. So if you have such two situations as given on this picture, in parallel, from big distance, effectively two electrons moving via this lattice will start to attract the cores, and so they can be seen as attracting themselves. So this phenomena is taking place at high distances, like 3,000 angstroms, 300 nanometers is typical size of Cooper pair. So the electrons interact with phonon, with lattice, and with vibrations of this lattice. And during this interaction, they create a bounded state. And when there's the electron state is bounded, it's natural to see that spin orients, they orient opposite spin, so they create quasi-boson. And so actually superconductivity occurs for the case of electron, not so small electron phonon interaction. Phonon is quant of vibration of lattice. So what happens is that actually superconductivity does not occur for the best conductors, actually, because very good room temperature superconductor, very good room temperature conductors, but not superconductors, need to have a low electron phonon interaction strength. So there is this binding energy that's measured in millielectronvolts. It can be in the range of 30 millielectronvolts for high temperature superconductors, and can be 3 millielectronvolts as for niobium or less. So usually these Cooper pairs are singlets, but also quite recently they can turn out to be triplets. So there are certain cases of superconductors that tolerate magnetic field. All right. So that's So that's this theory. We need to spend at least one lecture on BCS theory, and this will be necessary. So we'll see. All right, let me move on. So this is this materials, which high temperature materials, this family of superconductors. That's the year of discovery. You see, before the discovery of high temperature superconductors, low temperature superconductors has been detected. All right, and then, as I mentioned, at very high pressures, there is a family of superconductors that can have very high critical temperature, like minus 70 Celsius degree, pretty much. So not so even in Siberia, at some point, you can have the cooling problem can be solved quite easily. All right, and there is this family of discovery of there is boom of discoveries from from this Bednosh-Miller experiment, and you see certain types of high temperature superconductors. So usually they have quite complicated elementary cell as specified here. All right. Yeah, so let me now describe this conductivity. Well, it's a Drude-Lorentz equation for motion of electrons in metal. And simply saying, so this is given over here, it says that you have 1 over T is tau is relaxation constant. So the time, so you have this phenomenon as following, that you have accelerating field, electric field, and then sporadically the electrons start. So electrons are under acceleration of electric field, and when but there are phonons, vibrations of crystal lattice, or they scatter. So tau is characteristic time of scattering, and this is a measure of disorder. The higher the order or the more perfect material is, the longer is tau. And this tau is infinite for superconductors, essentially, or for perfect conductor. So what happens here is then when you integrate with time this equation, then you need to spot one thing, that there is a relation between vector potential and electric field. So if you integrate with time, so essentially for infinite time, you have the first equation reduced to the second equation, and then you can integrate with time, and then you get that on the right side is vector potential. So essentially it means that current density is proportional to vector potential. This is very phenomenological argument, which also, so you can start from Drude model, which is phenomenological model for materials with certain disorder, and then assuming this level of order in superconductor, you can make this argument valid. More sophisticated description of London equation is actually by Ginsburg-Randolph theory. Then you have basically current density formula as the same as for Schrödinger equation. In Schrödinger equation, you have current probability. And then under the assumption that order parameter is constant, you also get London equation from Ginzburg-Landau theory. You can also get London equation from PCS theory or Bogleov-Dijon theory, but I will leave it for later. So I'm just bringing you these concepts right now. You can also describe the London equation and relation of London equation with magnetic field. So you can have Faraday law and Ampere laws as given by formulas over here, and then you need to, in this context, you need to use the fact of that electric, this London relation, which was described last time on the last slide. So essentially, the current density is essentially proportional to potential density. And so you can have this relation as specified here, and it essentially brings you this this relation as given here. So actually you end up in this formula, which at the very last part of the slide, where the second derivative with respect to position is minus some coefficients times the same field. So then you can describe this decay of magnetic field entering the superconductor. I will come into details since today this is only time for phenomenological pictures. So at first I'm trying to bring you the context of considerations, and then we deal with the considerations in a deeper way. Okay, then if we talk about superfluidity, well, what happens is when you have liquid helium-4, by the way, Poland is a very big producer of liquid helium-4. I mean, there are some companies that exploit and exports this helium-4. Recently it becomes more and more expensive, but anyway, there's a worldwide race in quantum technologies that makes the price of helium-4 to be higher and higher. So usually it's used in closed cycles. So there's characteristic heat versus temperature. This is lambda transition is also present in superfluid helium. So usually when you, so this phenomena you can observe in 2.2 temperatures with helium-4, this transition to superfluid state. All right. I'm not going to go into details right now. Just this is basically what you need to have. You have helium at 4 Kelvin, and when you pump out the pressure of the gas above this helium-4, you can bring temperature of helium down below 2 Kelvin. So you can observe this lambda phase transition. As in regards to the story of superfluid phenomena, it's you can rotate superfluid helium, and at very low temperatures you have vortices. So quantized vortices, quantized magnetic momentum induced in the system. So it's a bit similar, not the same as in the case of superconductors. So this is Gross-Pitayevsky theory that describes this phenomenon. There is a famous book, Volovic, The Universe in Helium Droplet, that gives more insight into that. And at very last, I will mention about the last slide. So I'm going to mention about two fluid models of superconductors and superfluids. So basically, in superconductors, we assume that certain electrons are in Cooper pairs and certain electrons are unpaired. So those electrons that are in Cooper pairs, they create a liquid of superfluid electrons, and they are essentially quasi-bosons. So that's why there is no dissipation present. And when there is a fraction of electrons that are not paired, and they create a normal resistive liquid. When this liquid moves, this liquid generates dissipation, and it's quite similar assumption in superfluid helium. Certain atoms are superfluid state, certain are not. So two liquid model, normal fluid and superfluid. Normal fluid is resistive fluid. Yeah, so basically that's all for today. As about the books, well, there's Think and book also recommendable, but I'm a bit few theoretician, so I recommend Superconductive Metals and Alloys by Digens, and also Digens that has created this Digen book of Digen formalism. Also on Polish market you have Magnetyzm przewodnictwo and superconducting, so this is also recommended. And on the coming lectures I will also refer to the famous article by Frank Honori and Hugh, Superconducting Circuits and Quantum Information, when I will talk about architectures of Josephson junction. All right, I believe it's time to take some questions. Please give me some questions. Yeah, so I will.
So what is
Yeah.
what is the best book to get some fundamental understanding of superconductivity for someone that is not familiar with this topic?
Actually, it's not so trivial question if you want to answer this question in a very honest way. This Think and book is very lengthy, but it's recommendable. But let's say Think and book is a book both for experimentalists and physicists, while this Digen's book is a little bit more for a theoretician. I don't think that you'll understand superconductivity after one course of lecture attendance. I think that after one semester of attendance, you will get certain insight. I would say you will understand superconductivity step by step by certain solutions. So like London equations solutions, or Ginsburg-Randolph solutions, or Bogov-Dijen solutions. And understanding superconductivity is a little bit like understanding of quantum mechanics. You don't understand fully after one semester of study. You have a feeling, and you need years to master its understanding. So I believe it's a little bit like that. Tin Can book. Yeah, I will later. Yeah, I will. There is Shevchik. I have not yet perceived it in English. This Shevchik. Um, there are also Nobel Prize lectures that are recommendable. So let's say those guys that are Nobel Prize winners on given over here, and there is always Nobel Prize lecture that is supposed to be easygoing. So you have Josephson Nobel Prize lecture article. You can access. Um, but okay, if we talk already, I will try to bring you a description of BCS theory basing on Tinken book uh, and also this. So it will be combined approach from Tinken book and from Dijon book. Right. I'm not sure if I fully answered your question, but somehow I tried to. Any more questions or comments?
I would like to recommend also my few books. For instance, superconductivity and applications, superconducting cables, and a few others.
Could you write those books on the chat, please? On the chat. Please type the names of this book on the chat, Professor.
Yes,
yeah,
yes.
I would appreciate Sosnowski. Please write it on the chat so that we can see those we can have those references.
Chat. I have small problem with coming into chat. I can write you by mail.
Oh, that sounds good. So later I will.
Later.
If we talk, okay, let me give a second.
And if I am at microphone, I have small comment. If you introduce to superconductivity the lecture, I think that it should be explained difference between induction and magnetic field, because we talk about critical magnetic field, but in fact it's critical magnetic induction. It's not everybody remember about that. There are two other things, induction and magnetic field, because in fact in type 1 superconductors expulsed is magnetic induction.
Yeah, so
in fact it's important.
Yeah, so thank you for bringing this. So you can also say that.
And still one remark, if we observe here BCS.
Yeah, Professor, could you re-say your Sosnowski? Could you re-say your last sentence? Can you repeat? Hello.
Yes, of course. If you hear me,
yeah.
I would like only to remind that Professor Cooper has died a few months ago. So if we see his photos and talk about his theory, maybe it's interesting to say that he has just died.
I see. Okay, this is sad news. Yeah, so one second. About this book on superconductivity by Tinken, there is actually one chapter is for free. You can download it. I will. It's already on the chat. Yeah. So if we talk about superconductors, yes, exactly. The superconductor is ideal inductance. So it's a inductance with no resistance and no capacitance. So in a very real way, it, in yeah, superconductors can implement the inductances in perfect way. And yeah, so description of superconducting phenomena by means of inductance is also quite useful. Yeah, so and then now I try to search for these books. Uh, uh, your books of Professor Jerzy's. Yeah, I try to come to these books which you have mentioned, superconductivity, so people could. In the meantime, okay, the energy transfer is not that easy. Uh, so thermal gradients basically doesn't exist in superconductors, but because it's like the whole superconductor is like one wave function, and you will see this wave function by means of Ginzburg-Landau theory. I tried to yeah, this yeah, so I will just yeah, I will come to these books by Professor Sosnowski by I will by email. I will let you know. Will let you know. Also, you can have my email because this lectures has been announced on this research seminars at Gmail. So you can have my email over here. So please feel free to contact. Okay, any more suggestions, remarks?
I recommend, excuse me, my books because in them there are original equations. It's given original procedure how obtain this phenomenological equations on superconductivity. For instance, vortex structure, etc.
Yeah. So I'm trying to access the books by Professor. I think I already have them. This yeah, so Nadprzewodnictwo i zastosowania Sosnowski is one of the book by Professor to that I have already spotted during Google search. Yeah. Any more comments? Eric, any more comments or suggestions? Or Radosław, any more comments or suggestions?
That's it for me.
That's it.
Yeah,
okay.
I think so, yes.
Already come until yeah, so there's another book that shows yeah. I think you can access this in the library. I will yeah, you have this book on the chat which I specify. All right, so I hope so next on the coming lectures will be more mathematical, so it will just warm up. All right, so thank you for your attention, guys, and see you next week. Thank you. Bye-bye.
Thank you.